All right, I'm going to get started, and then I'll let people in as I'm doing the intros. All right. Welcome everybody to April's DataWorks Maryland meetup. Super excited about this. It's a very relevant topic, as everyone kind of saw in all the posts. It's related to the COVID data and some of the interesting work that John is doing down at Johns Hopkins. So, as usual, before we get started, I just like to always thank our partners and sponsors and few brief announcements, and then I'll hand it over to John. So this is about the role of data during apocalyptic times. Everybody knows what that means with COVID. So partnership-wise, we got a few companies that helped us over the years. Variant Technologies is one that's been there from the very beginning. They do a lot of data science, software engineering, supporting various government agencies. If you're interested in learning more, please reach out to myself or go to their website directly. ClearEdge is another government IC support company. They do a lot of data science and analytics. They used to run and I think they still do, the Accumulo Summit. We've been in discussions for a while about potentially doing a conference through the meetup. Another great company. If you'd like to learn more, reach out to them. I know they actually have an active internship program if you're interested in that. Captivation Software is a new sponsor, actually a friend of mine. Great small company and doing a couple little different things. They do some actual software, open source stuff, and support some of the customers up north in Maryland. If you'd like to get in touch with Dave over there, you can ask me for an introduction or go reach out to them. Sorry, hold on one second. Aries Ventures is our company. I don't usually focus too much on this one, but if you're interested in learning more about what I'm up to, I'm always willing to talk to people about really anything, industry, meetup, anything that you would like. Just reach out to me either through the meetup or through the website. All right, brief announcements. So I scheduled a pitch event that still the turnout's a little low, so I'm trying to figure out how we might do that. Really, if anyone knows anyone that would like to talk, really, you get 3 to 5 minutes to kind of pitch anything you want, your project, yourself, your ideas, your company. It's really meant just to bring the community together and see if people are doing anything interesting. We've had a couple submissions, anything from professors to companies, and I would love to see some more involvement. In June, we have a really pretty cool workshop that's going to be coming on graph analytics. It's a speaker that had spoken before, and he does an amazing job walking through everything. So if you want to play around with graph analytics, I definitely would tune in for that. And in July, really excited to have a speaker actually that's supporting a product called Datawave, which is something that came out of the agency and something that they open source. And it's really built related to like Accumulo and big data storage and how they handle that. So if you're interested in those kind of topics, definitely look for those coming down the pipe or coming out. We're still doing the newsletter. I have someone helping me now, so it's going a little quicker. And if you know anybody that's interested in speaking or sponsoring or working with us, just reach out. If you want to be involved, just reach out. For some reason, this thing, Prezi, is not cooperating today. And with that, so John is the Chief Artificial Intelligence Architect and Applied Information Science branch head within the Asymmetric Operations sector at the Johns Hopkins University Applied Physics Laboratory, which just rolls off the tongue, John. That's an amazing title. I got the pleasure of being introduced to John a while back, and we've been going back and forth on topics. Honestly, he had so many interesting things he could have talked about, but this one felt the most appropriate, and he felt it's something he could talk about really well. So with that, final logistics. As for questions, please type them in the chat, or if that's on YouTube or Zoom, I will capture those, moderate those at the end. At the very end, for those that hang around, I'm going to do a drawing and give away some O'Reilly books. So I'm just going to do a random number and go down the list, and then I'll ask you to email me, and we'll get you a book for free. With that, John, you can take control of the screen. I will mute myself, and it's all you.
Okay, you see my title slide, Jason?
Yes, looks great.
All right, great. Hey, so as Jason mentioned, and good afternoon, and thanks for taking time out on Saturday afternoon to listen to my story. And really, Jason and I were going back and forth for several months, and I was really thinking about a cool AI talk. But I really landed on this topic, and it really comes down to, we've all been impacted by this, and I chose the title because in my experience, this is a crisis of a lifetime, and I've worked in national security for decades, and this is even more profound of an impact than my experience in 9/11. So pretty serious business, serious times, a lot of impact to the globe in this space. Now, maybe to lighten things up a little bit, the way I've organized my talk, it's around three equations, and as everybody loves equations, and I'm an engineering nerd, I organized talk. So just a little bit about me. My story begins in 1985, and I graduated from Penn State with a double E degree, and I accepted a position at the Applied Physics Lab. And at the time, I was accepted into this special training program. And the problem, however, was the program didn't start until September. I graduated in May, and here I am. I'm this broke college student, and I went back to my recruiter and I said, hey, I really need a job. I mean, I was so desperate. I collected the money from all my roommates my senior year for the utility bills, and I said, I'll pay the bills once I get a job. So I was pretty desperate. And so the recruiter said, hey, come, we'll give you a summer job. And so that leads me to equation one. So any guesses on this equation? Probably not. But what this equation is, it's a equation used to calculate the gain of a phased array antenna. And it is needed to determine if you could communicate with a satellite that's 22,000 miles away from a ground terminal. And the way the equation works, it takes the gain of each element in the array, that's the xn, multiplies it by the weight that's set for the gain, and then essentially you could think about setting those weights as kind of a flashlight on the ground for that equation. So back to my summer job. The government owned two systems that would calculate whether ground stations could communicate with their defense satellite systems, and for global communications. And the problem at the time was the systems were given different answers. And my job was, hey, John, go figure that out. And the importance of these systems is they would support military operations. So when units deploy, they need communications, and they could go anywhere on the globe. So will they have communications when they get to a certain location? So for today's world, and many folks, just imagine if these calculations weren't right, they would go somewhere and they wouldn't have internet connectivity. That's pretty tough. So it turns out I dug into the algorithms and the systems, and this gain equation was part of both systems. And they had the equation right. Both systems were using the same equation, same algorithms, but they calculated Y different. So what was going on? What was happening? Well, what was really happening, and here was the problem, was one system used the VAX operating system. I don't even know if anybody out there even remembers VAX operating systems. I do. The second system used an HP 3000 operating system. And the original file, so back to that X vector, that file was built before the satellite was launched. They would take the satellite out to an antenna range, and they would measure gain patterns for the array antenna. So you end up with this big matrix file, and that file was loaded on an HP 3000 computer. So that was the original system. Well, the issue was, and some of you may remember this, if you've ever worked on these systems, the HP 3000 operating system, it would write bytecode from right to left versus left to right. The VAX VMS system would write bytecode from left to right versus right to left. So essentially what happened was the system on the VAX read the file in the incorrect order, and that was causing problems. So that was really early in my career, the importance of data. And so for decades now, in the back of my mind, I'm always very aware and focused on data problems. So let me fast forward another 15 to 20 years. Any takers on this equation? Well, some clues with the picture. That's Larry Page, Google search. This is the this is the PageRank equation. Very simple equation to come up with the rank of a web page view based on the links that that web page would have with all the other pages linked to it. And very simple equation. They published it in 1999. Sergey Brin was a co-author with some others, the creators of Google. But the important part of this equation is this really had a profound impact on how we deal with data. The whole big data era, the NoSQL era, all that, some of the things that Jason was talking about earlier, all came out of a need to, I need to calculate a page rank. I need better data architectural approaches to do that. So, the big data era came in, and it's been used for a lot of different industries, domains. So what I want to do now is focus, again, building into COVID, on health and medicine. So I want to speak to a partnership that we have at the Applied Physics Lab with the Johns Hopkins Hospital in medical school. And they have this concept of precision medicine. So if any of you work in medicine or have experience with medicine, the way we deliver care these days, it's a lot of trial and error. So we give patients that blue pill. It's trial and error, like, okay, will that pill work or not? We really don't know. We try it and then look at the effects. The idea of precision medicine is if we could group populations, like populations, together and understand that the blue pill will help those 3 individuals. It won't help the second individual, but they really need the yellow pill. And then the last 2 need the green pill. And that's really the idea of precision medicine. Can I collect data on like populations and give treatments that would benefit them? And the way to go about that, and this was an initiative we started 4 years ago, is how do we make data more readily available to clinicians, to researchers, to people doing care delivery, so they could understand the context of that patient into a broader population, as well as, and you see on the bottom, you see a couple charts, but what they're really saying is give the researchers, give the clinicians a broader set of data. So when they look at a disease or look at a patient, they could come up with better treatments. And the way this manifested itself is something at Hopkins, and you could go out and Google this and find a whole lot more information, but it's the Precision Medicine Analytics platform. And I was involved with this in the beginning in working with Hopkins. And if you peel back the onion of this analytic platform, a little secret, it looked a lot like an analytics platform that we developed at APL for cybersecurity. So again, it was this idea of analytics platform, horizontal data layer, a horizontal data layer. This got manifested into a data commons. So pulling things out of electronic medical records, radiology systems, genomic physiology, so equipment in ICUs, for example, and pull all that together into a data commons in a research environment. So if a physician is looking at, and at Hopkins, they have these precision medicine centers of excellence. So you see a whole bunch of diseases here. So if I want to do research in prostate cancer or MS, and I need to get that population, all the data around that, that's what the PMAP, Precision Medicine Analytics platform, will do. And so what you see here is once we built out that analytic platform focusing on the data, and it took a couple years, and it was a challenge because the physicians and clinicians and leadership at the hospital says, show me some results. And we said, we have to do all the data, all the data engineering, data munging, data wrangling, and doing the projections of all that data into, originally we started with a Hadoop ecosystem. So what we have, once we created that, now we have these analytic toolboxes that are now used. And I'll give you a couple examples of, and I'll build this slide of some tools that are out there. So this is natural language processing, and you're all data folks out there. So I think you appreciate structured and unstructured data. You may not appreciate, on average, when you meet with a physician, they only spend about 20 minutes with patients. And we do have these electronic medical records. But, one of the challenges with these medical records is, for example, I've been a patient now at Hopkins for 3.5 years. Unfortunately, I have a rare disease. Fortunately, Hopkins is in my backyard. But if I was to print out my medical record today, it would literally be close to 400 pages, right? So if I go walk into the clinician, here's my 400-page medical record, and they have to go find something, it's quite challenging. And one thing that happens at Hopkins is people come to Hopkins usually when they're really sick or they have some rare condition. So they come to Hopkins with all their medical records, and the clinicians have to get through all of that. So the one example I show here in the lower right was one of the early things we did because prostate cancer was one of the centers of excellence. And we just created some pretty simple NLP tools to go look for something called the Gleason score. So in cancer, different cancers have different markers. The Gleason score is created during pathology. They take tissues, they stain tissue, and they come up with the growth rate of prostate cancer. That's the Gleason score. The problem is Gleason scores could be written all different ways in medical records. So this was some of the analytics we built once we get the records in, so we could throw machines at it. We also do a lot of work in imaging analytics. So this is some work in MS, looking at things like MRIs. And one thing about disease is how do they change over time? And so we've created some tools that will take static imagery and look at how things change over time. At the Applied Physics Lab, we do a lot of work in national defense. So a lot of stuff we do with radar, we have a rich radar history looking at how tracks change over time. You could apply some of those lessons and ideas into the medical field. So where are we today with PMAP? We started out with an initial architecture. Again, conceptually, it's all about a horizontal data architecture, pulling in data sources. We started with a Hadoop ecosystem, but like with most data architectures, you always want to be evolving them. Hopkins has a very deep partnership with Microsoft. So we're now sitting into a Azure instance where we have our data commons, we have our projections of data. We could bring data into Jupyter notebooks, so you could run R, Python. It all sits within this safe desktop environment. It's all controlled, just not anybody could get access to this data. We use, again, we still support MS SQL. We're using Databricks quite a bit. We could stand up Kubernetes services all within the Azure. So if any of you work in Azure ecosystems, you're probably deeply familiar with the tools. Now, the talk was about COVID, so let me then maybe tie PMAP to COVID as an example. So this was a recent data set that's been created by Hopkins. So it's called JH Crown. And because we created the analytics platform, Hopkins was, they were able to create this projection of data into PMAP pretty quickly. And there are several studies now. So a clinician just has to go and write their IRB. I'm kicking off a study with this data as well. But we have 5,000 patients and growing. They've either been tested, result positive or negative. They have a diagnosis of COVID-19, or they have suspicion of COVID. And then it's a really rich set of features that's available, over 100 features, demographics on the patient, patient encounters is what when they meet with a clinician, what's in the notes, things like that, what medical treatments they've had, what lab results, be it chest x-rays, blood work, things like that. So in terms of COVID and the fact that this analytics platform was there, at Hopkins, we've been able to curate this really useful data set that is now being used by researchers in COVID. But I want to shift gears and then introduce my final equation, and this is the equation 3. So I really didn't know much about this equation until about a year ago when COVID hit. So this is called the Seer Equation. This is what epidemiologists, public health people use, disease modelers. It's a very simple equation, right? You take a population N, they're either susceptible, exposed, infectious, and recovered. It's Saturday afternoon, I want to keep it light, but you'll see other versions of this with the other state where you go from infectious to death. I didn't show that here. Very simple equation. So why is disease modeling so hard? The problem is the factors, they're all the Greek letters in between the different states. Is how do you calculate those, right? You could count numbers of people in each state, but if I'm going to do a prediction, I need to be able to predict those transition factors. And that's been one of the big challenges. So now what I want to drill down, and I have the pleasure of dive deeper into 2 projects, and I call these 2 data projects, and they were largely data projects that really had an impact on the globe. So the first one on the left is, I'll call the dashboard, and this started out at Hopkins at the Whiting School of Engineering, but within a couple weeks, APL got involved with it. And then the second project I'll call the Data Analytics Task Force. This is where a team from APL basically were deployed to go support an interagency activity with FEMA, ASPR, and these things they call NRCCs. When a crisis occurs, these get stood up by the government. Now, I want to give credit to one of my colleagues, a guy named Jeff Freeman, who has deep experience in public health and emergency response. And prior to COVID, he conceived of this idea of a disaster response corps. And the idea really came out because at the Applied Physics Lab, we're 6,000 technical folks. And I mean, there's a discipline, every discipline is covered at APL, from materials to biology to sensors to data analytics, data science, AI. Last night I'm going back and forth with a microbiologist on AI for microbiology. And so the idea is, hey, when these disasters happen, how could we mobilize this technical talent at the Applied Physics Lab and help them, help typically the government, but in the other case, this was the university, to bring to bear all this technical expertise to a national problem. And if you go read the mission statement of APL and what we try to do, basically we're there to solve complex problems, be it research, engineering, analytics, that present critical challenges to our nation. That's why we exist in our 78-year history, to really be there when there's a national need. And I will honestly say COVID was probably, the crisis of a lifetime. So let's start with in the beginning. And I know Aaron's out there, and this is the way he tells the story. But it all started with coffee. And the picture there first is Dr. Laura Gartner, who is the co-director of the Center for System Science and Engineering. And she was meeting with her PhD student, Frank Dong, located below her on the right. And Frank recently joined the CSSE, and they were having a talk, and he had a personal interest in what was happening in China because of friends and family and friends in the impacted area. And he also had a strong background in GIS and data visualization. And so their interests melded together. And I should say, Lauren is an expert in infectious disease modeling. So they recognized the importance of data. So they built the first prototype of the dashboard. Lauren sent out a tweet, and that tweet went viral. So basically what happened was, in week one, right, this was picked up by media, it goes viral, and it went from, the dashboard went from a few thousand page views to 10 million hits per day in the first week. So this thing went off like a wildfire. And really it was, everybody's out there seeking data. Well, the early data operations that was put together by Laura and Frank and their team, right? And this is what you would expect, if you're in grad school, right, and you're doing research. All right, you're going to go collect a lot of data. You're going to do manual data curation. You're going to throw data into Google Sheets, and you're going to push out this dashboard. And it was really this manual data process. And as this thing was taking off, they were running into problems like access problems with Google Sheets. It just couldn't scale to the number of people that were coming for this data. So in a short amount of time, an early partnership was created. So we had the Whiting School of Engineering, Laura Center. There was a relationship with Esri for geospatial expertise and serving things up on maps. The Sheridan libraries were involved. This is one thing I've learned in my experience in data science. Libraries play a key role in data science and library sciences, but they were there to help us with infrastructure. And then back to Jeff in that disaster response corps, a call went into APL and said, hey, can you help us with this, this dashboard thing? So this was the early partnership. So our team, our engineers and folks who work in my branch, and a shout out to Aaron Katz, who is out there, became the lead for this. And essentially, we started putting together a more resilient data pipeline and data architecture for this. So, going out to global web pages globally, pulling out data, creating a pipeline, pushing things out to GitHub, and then also recognizing that many of the news media, they were going to the GitHub site, pulling the data and putting it out on websites as they saw fit. And then with the Esri team and the Hopkins team, basically we were running the dashboard as well. And then in this picture, you see the initial architecture. So in the beginning, there were about 25 sources the team was pulling from. They were doing automated project generation. So they were, as much as they could, basically pull in data automatically. But one of the problems was we had an automated pipeline, but there wasn't a whole lot of error detection and anomaly detection. And the data would go out, and it would go out into the GitHub repository. And to date, right, this thing started last January, February. There were like over 300 GitHub instances. So data would go out, and somebody would see something, and they'd say, go fix your data. And it really started to tax our team. And they were up in the middle of the night, because this was a global source, right? So across the globe, people are all in different time zones. And one of the interesting articles that's out there is where the headline in the middle, where the COVID-19 map basically erased Palestinians, right? So again, we were pushing data out there, and we ran into things, for example, Crimea, right? Where do you count that? Is it part of the Ukraine, or is it part of Russia? WHO was considering it part of Russia. We had to go to State Department norms or standards, and so we assigned Crimea to the Ukraine. So these were a whole bunch of issues that this team was dealing with in the heat of the moment. And many people, and I think many of you who work in data appreciate this, but other people say, just go get the data. Why is it that hard, right? Just easy, just go write some Python scripts, throw it in pandas, you're done. Well, the problem is reporting. It's inconsistent, it's constantly changing. We run into the scaling problem. We run into, and this is what some of the team was dealing with, a website would go down. They were pulling data from a website, nothing showing. They'd get a Slack alert 2 o'clock in the morning. The team would have to go in and fix these things. And then we'd run into interesting things. So here's another example where in public health, we have state public health departments, we have county public health departments, and we had a case in Texas where we would take reporting from Harris County, and then we take reporting from the state of Texas that would report on Harris County, and these things didn't match. So we had to create anomaly detection algorithms to work through that. Also, when we got into measuring positivity rates, everybody was doing it differently, right? So what does positivity rate of 5% mean in New York versus Alabama versus Kansas? They all had different meetings. So these were all things the team had to work through. So the architecture continued to expand. So this is their Gen 1 architecture, up to 100 sources. Again, automated product generation, and then building in automation for anomaly detection and correction. And this was an important thing they needed to do before they pushed the data out. However, to the right, there was still a manual recovery process. So the team, they would get emails, they would get incidents reported on GitHub, they would get things on their Slack channel, and so they had to resolve many of these things. And demand just kept going up. I mean, when we really started, things started heating up in the April timeframe. Just the number of requests per day just kept going up, so had to deal with scaling. So they had to create their Gen 2 architecture. And so they had to start parallelizing a lot of things for automated collection. And this really helped quite a bit. And then we had to have parallel data fusion processes. We still had our automated detection and recovery. Again, still have people in the loop on this. We never fully were able to not have that part of it. But through our Gen 2 architecture, things started to get better. In fact, Aaron, who's out there, he liked the Gen 2 architecture because it basically allowed him to take a day off. Poor Aaron worked from February through August, 7 days a week, making sure this thing ran. And it wasn't until we got to Gen 2 where Aaron was able to take a day off. So that was a good thing. So this was the journey of the dashboard and the data behind the dashboard in the team that did it. And also to make this happen, it does take investment, right? This is not just a couple people, throwing around some Python scripts. So there were some foundations involved. So a Greek foundation provided Hopkins funding. Bloomberg, there's a strong tie between Hopkins and Bloomberg philanthropies. We even got some money through the Joint AI Center because on the DoD side, they were dealing with the same problem. Where are hotspots? What's happening? They have military bases spread out across the world and in the US. They do a lot of exercises. So they helped invest into the pipeline where we started to pull in county data. And then industry came in a big way and really helped with licensing from Slack, GitHub. Amazon was giving us some free credits along the way. So that was our Hopkins journey. Now let me shift to the second project. And this one was really our government response to COVID. And really in this journey, this is an interesting one because it went beyond just providing data for people to consume. It was really helping the government make decisions on what to do. And as we went through COVID in the pandemic, different conditions, and I call it riding the waves of the curve, things changed over time. And so this story really begins on a Sunday afternoon, and I was more involved with this project. So if you remember my colleague Jeff, he works for one of our executives that runs our National Health Mission area. So I'm home. Where else am I going to be? You know, it's March of 2020. So you're home, social distancing. The other thing I went through at that time, I had broken my leg. So I really wasn't going anywhere. I was home in my boot. So why not answer a phone call from an executive at APL on a Sunday afternoon? And I answered a call from Cezanne, who's the executive, and she's like, hey, John, do you think you could come up with 10 to 20 people to work a FEMA project for COVID response? And I'm like, well, first, whenever I hear FEMA, I always think of FEMA trailers, and I have a lot of old camping jokes about FEMA trailers. And I'm like, interesting. And I said, hey, I think this is going to be a difficult thing to do, but give me a day. Let me see if I could track down some staff, and maybe we could send some staff down to FEMA to see what's needed. So we grabbed some staff on Tuesday to go down to FEMA. By this time, we're looking at this problem, working with the government, and they're like, 20 is not enough. We think we need 60. And part of what we did as part of that team was, hey, let's make sure we send some data architects, data engineers, and that was one of the things we did. And so one of the first things we did, and I should also say, in the matter of about 2 weeks, so go back to the applied physics lab, what we do, we're focused on mission, and this really surprised me. We had, in a couple of weeks, we had about 69 FTEs of labor going against this. If you count people, right, some people were part-time. We had close to 100 people working this. When we were at APL sending people home, go home, work from home, government places were closing. We had 20 people going down to FEMA, to the NRCC every day. Caused some interesting questions, but again, there was a team that went in here. One of the sub-teams was the data sourcing team, and this team was basically, where do we go get data, right? We need data, right? And early on, when we were riding the waves, one of the big things for the government was, back to the FEMA influence, we have ventilators, we have PPE. Where do we send them? What do we do with them? Supply chain issues. So where do we go get data? There, we were looking at all kinds of data. So there are government systems like NSSP provided some data. USA Facts is another area we leverage data. But we also looked at things like Google mobility trends. One of the problems with Google mobility trends, it lagged 5 days. That was too long of a time. We need more real time. We looked at, there's a company out there, Kinza, that does these smart thermometers, right? Everybody was taking temperatures early on, and then they would have the back end with all the data. We looked at that. However, it was too sparse to help some of our analytics in modeling. So again, we were trying to find data wherever we could find it, and it was quite the journey. Now, with that said, in looking for data, and on the next slide, I'll talk about things got a little better, but we still struggle with modeling. So what you see on the left is in the Zoom call, is you see that is General Mark A. Milley. He's the chairman of the Joint Chiefs of Staff. He's the top-ranking military person. So he came to visit APL in April of 2020. We had experts from APL. We had experts from the School of Public Health, a lot of the folks who were in media talking about this. And General Milley had a problem. I run a military. Where could I deploy forces? How safe are my forces? Tell me how many people are going to be infected 6 months from now. And there I am. I'm up in the left corner, and I had to speak to the data problem. And I'm like, sir, we just don't have good data. The best we're doing right now is we're able to project a couple weeks out. I should also note it was a fun time for me to present to a 4-star general wearing shorts. So I was on a Zoom call, had a nice shirt on, but I had a broken leg and I was wearing a boot. So I figured I could sit and brief a 4-star in shorts. So that was kind of cool. But if you look to the right and where we are today, we still have a modeling problem, right? So this is from CDC, and they do ensemble modeling. And you could see some of Hopkins models in there. You can see one of our APL models in there. And we're doing projections. And then what happens, CDC runs an ensemble across all the projections, trying to come up with our best estimate of case counts. So it's still a challenge, still a problem. Data is critically important. However, the data changes, right? We talk in disease modeling, we talk about NPIs, non-pharmaceutical interventions, right? These are mask mandates, business closings. As those change, they change parameters back, if you remember, back to that Seer model. So still a challenge. But let me highlight some of the decisions that we've made, that we've had to deal with, right? So this is my point. You start with a decision and then figure out the data. So early on, we were all about PPE. We created some initial PPE calculators. I think if you looked at the models, you'd probably be like, this is the Johns Hopkins University creating these models. They were very simple, but part of it was data. We had to go to SMEs. We had to find research articles. How many gloves does a hospital consume in a day, right? One of our researchers, Matt Kenzie, he created something called the Bucky model. It's named the Bucky model because his dog is named Bucky. So he has a model based on the Seer model, and he's using case and death counts, hospitalizations, and these NPIs. Again, a good model. It's actually been used by the UN for some global forecasting. And then finally, another one of our researchers created the gecko model. It's called the gecko model because his son is really into geckos. But what happened was the Bucky model and some other models, we were trying to predict hotspots. When the whole nation became a big hotspot, then it's like, oh, now we have to worry about hospital capacity. So we had to have a model. You'll see some of the data feeds that we were looking at change. So this is all about decisions to data. And then finally, I want to bring it all together, right? So I mentioned the two projects, over here, dashboard, Johns Hopkins University, over here, government response. And what happened over time, these things came together because on the dashboard, we continued to create generations and add new things in. And then the CDC and the government response, they ran into some issues with transparency of some of their data feeds. They said, hey, could we have a feed coming to us? And what's really cool about this pipeline that you see is we have now our autonomous collection. We have our anomaly detection recovery. We have pretty sophisticated ETL where we do the curation. But now we're able to provide data feeds to different folks who are asking different questions. So on the university side, it's global cases, death counts, testing, vaccinations, demographics, policy. For CDC, their focus is in on the US, and they really need the case counts and death counts. So just looking ahead a bit, so where are we going in the future? I'm really excited about CDC is really looking at data modernization, right? I'm sure we'll get some questions as to why wasn't this built before and why didn't it exist? And the reality is public health, and not that I've worked in the field for a long time, but I've worked over the last year with a lot of folks in the field. If you go back like 15 years ago, there was a big investment in public health, but then it waned over time and it just atrophied, and the data world was moving quickly. We also, even in conversations with Jeff Freeman, who lives in this space, nobody expected a pandemic of this magnitude, right? We planned for it, we knew it may happen, but nobody ever expected it to be this profound. So that's good news. And then some research that involves Hopkins and APL. One thing that I'm working on is we call it PanNet. So one thing I've learned is, when a new pandemic or outbreak occurs, we go to the last one and pick up all our models. So PanNet is really looking at gold standard integrated data sets. We're just starting this research. And I want the PanNet to be profound like ImageNet has been profound for AI and computer vision. So how do we bring together all these disparate data sets and create some really high quality gold standard data sets? I'm also excited about homomorphic encryption because we also know we can't share all the data with everybody like JH Crown, it's protected data. However, if I could send my analytic to the data through encryption, calculate what I need to calculate and bring an answer back and use homomorphic encryption, that would be great. And then finally, just some of the lessons to leave you with. It's all about decisions to data, right? So what questions are we trying to answer? That's what we lived as we went through COVID, and that changed the data we would look at, the data we would focus on. You really do need to plan for data ecosystems. You're never done in this space. So the dashboard, PMAP, and even the government response. And then, data quality is resource intensive. I mean, my experience in data science, in AI, 50 to 80% of your resources goes into the data, and we've learned that here again. And then finally, and most important, it takes a village to do this. And this is my last slide. I do want to acknowledge this is the APL village that was behind all this. I mean, I'm proud to be colleagues with these folks. Some of them are on the line, and they were working 7 days long hours. As a supervisor, I sit there and approve time cards, and I'd sit there and approve time cards like, 160 hours in 2 weeks or 200 hours, right? So this is a great team. Many of these folks went down to FEMA when people were going back. So I'm just proud that I could be affiliated with these people. And I will stop there and take any questions.
Thanks, John. That was awesome. So we're starting to get some questions. I'm going to try to bucket them as best as I can. I guess I'm going to start with a question that I actually had. The quickness that you had to react seems pretty astonishing, and I was just curious. Have you ever seen anything like this? I know your experience kind of goes across a lot of different areas, but have you ever seen anything where decisions had to be made so fast and things ramped up, and then had a follow-on question depending on your answer?
No, I mean that's why I gave this why I gave it the title I did. It was astounding speed, the decisions that were being made, and I've learned a lot about public health. There's these teams, I forget the exact names, but I think they're affiliated with ASPR, but there's government people ready to go on a plane, and it's like, where do you send them? So you're on a daily basis, you're making these decisions. I mean, there are quick reaction things in my experience in national security, but generally there's a whole lot more time and planning that goes behind something. I mean, there's a great quote the team uses, and I know when Aaron talks about this, we were basically building the airplane as we were flying it. So, yeah.
So how did you get a bunch of technical people to agree on the platform and tools that quickly?
When you're under that pressure, there's little time for what we would call collegiate debate. I mean, it's kind of, pick things up and move as quickly as you can. So, yeah.
What was the timeline between generation 1 and generation 2?
Let me go back and look.
Because I think you mentioned August. I wasn't quite sure if that was like a couple months or not.
Yeah, August generation 2 was fielded, and generation 1 was, I believe that was like February.
So did you guys get started on generation 2 pretty quickly and then develop it over a couple months, or?
No, it turns out it was the same people running. This goes back to the comment of building the plane while you're flying it. So the same team that was, running generation 1, dealing with, the daily request or daily problems. They were also trying to find time in their busy day to work on Gen 2. So we didn't have the pleasure of two different teams. So, yeah.
So there was a couple questions about, and I think Aaron had given an answer, but for those that aren't reading, he had said the Coronavirus Resource Center has the vaccine data and associated analysis. The same pipeline is providing that data and is being published on the GitHub. So there was a couple questions about, are you guys working on, doing similar things for vaccines and showing how vaccines are being utilized and impacting various populations? Do you have any? I wasn't sure if you had anything to add to that.
So Aaron answered the vaccine, and I had it in a slide. So that data is going into the pipeline. On the government side, there is some analysis looking at that. Right. Again, I think the vaccine data is it's important from twofold. One is there's a supply chain issue, right? And then the second is how effective is it, right? But I think we're still too early in the modeling world to really completely understand that. So, but the data is out there being published.
Are you doing anything to track some of the variants that are coming out? Is that more stuff that you're looking at?
That's a great question. So I just spoke to one of our analysts the other day, and we were one of the challenges. Again, this gets back to timeliness. Um, the variant data is quite data. So you could go to CDC, their data hub, and if you look at the variant data, it's actually about a month old. So for what we do for the government, that's too stale at this point for our team, right? It's not to say somebody isn't looking at it. So yeah.
Okay. So you had talked about the Crimea issue, and there was just a question. Was there any other examples? And in particular, the person was asking about, some of the data coming out of Florida, I guess was questioned, the accuracy compared to independent studies. Were you running into any other issues with like domestic data that we had?
I would say, and Aaron's online. Aaron could probably write a whole book on that. Yeah, I mean, I think there was constantly data anomalies out there, right? And some of it is people make mistakes in reporting. Some of it is reporting is lagged. Like a public health department may not report until Monday, right? So reporting over the weekend, you may get some anomalies in the data. So
Yeah, I can only imagine the type of data you're dealing with. Um, are there any other products or projects that you were tracking that you were impressed with? And in similar dealing with COVID and stuff.
yeah, so I would I'll give one example, and Jason, this may go back to our mutual colleague Ian McCullough, who works for Accenture, right? Um, he was doing some interesting modeling, and again, remember back to decision to data, and then what models do you need? Um, they were supporting big companies. I can't remember the names, but large global companies that had the same problem like the government, right? So, what does this thing look like? What does it mean to supply chain, to the company? What does it mean to their plants, their employees, and all that? So I was impressed with um, their modeling was trying to answer different questions, but what was impressive was even um, industries were being faced with this and needed to data and needed to do modeling. And I'm pretty sure Ian was pulling the JHU dashboard data. So
Cool. So, I think this might be the last question, actually, and I think it's a good way to end. Knowing what you know now, is there anything that you would go back and do differently, or change? And then I'm going to add my another little piece. Do you think we're better positioned now in case this happens again, based on what you're seeing with data? I guess from this perspective.
oh yeah, we would go back and I don't think there's nothing that could have been changed going back to the beginning. Because again, I think nobody expected this thing to be as as profound as it was. In fact, I listened. There's a really good podcast um, that I listened to this morning from The Economist on, it's still not clear what the source of the virus was, right? So given all the unknowns from last December of 2019, um, I think we'd still be in that same position. I can't think of anything that we would have done something maybe a little bit different, right? And I think each of you out there personally could just reflect on, what your experience was, right, when this thing was, unfolding, right? I mean, um, it caused a lot of angst, and I mean, even myself, it was like my boss said, "Hey, go home." Right, I have a comorbidity. Go home in March. I never want to see you again. Right, that was kind of the tone. So it's really, I just can't fathom. Now, with that said, I think this was a wake-up call to the public health community, and I'm hopeful for initiatives that will help. One of the big challenges that we have is, and it was in this space, right? It's you could be infected and be asymptomatic, right? So many of our surveillance systems really don't find you until you're symptomatic and you're sick. And so, how could we start looking for things sooner, right? And that gets into a lot of in some work. I'm an AI person. I'm not a biologist, but I'm reading a lot of AI papers related to biology, right? So how could we speed up the front end of that and maybe find viruses faster and understand the global spread faster? So and there are initiatives. You could go to the CDC. Right? They want to modernize data. Let's get better data. Let's get data standards. Let's help states. That's the other part, right? This is not just a U.S. government thing, right? We have um, public health departments, state and local level, right? They need some help too to be able to provide data in better ways, and then also, be able to track viruses much earlier and more quickly. So, yeah.
Very cool. So that was pretty awesome. I mean, I'm truly amazed at how quickly you guys stood that up and how important it became. Um, with that, I'm going to kind of wrap it up. Thank you so much, John. I think that was amazing. I am going to do a quick book giveaway. So if I call your name, please shoot me an email so I can get you a free book. Let's see, 3, 6. So Howard Rothenberg, shoot me an email. And Laura Adams, shoot me an email, and I'll get you a book. With that, I hope everyone has a good rest of their weekend. Thank you so much, John. I hope everyone can tune into the next meetup. And if you ever need anything, John, just let me know.
Okay. Hey, thanks. Yeah. Hey, Jason, we'll have to follow up on trails.
Yeah, definitely. I love to hear about the mountain biking.
Yeah.
All
No
right.
worries.
All right.
All
Have a
right.
go, man.